Okay, so welcome to the Explore Practical First-Hand Experience in Using SNOMED CT, and that's the stream of the SNOMED CT Expo 2021. My name's Ian Green. I'm the Customer Relations Lead for Europe and also the Global Clinical Engagement Lead at SNOMED International, and I'll be moderating today's session. So please use the live Q&A in your AirTouch device to type in your questions to the presenter, and all questions will be answered at the conclusion of the presentation. I'm now pleased to introduce Gloria González, who's from BTAC, who'll be presenting today to you and presenting integrated, relevant phenotype and genomic data in EHRs with SNOMED, LOINC, and other genomic standards. So Gloria, please proceed.
Thank you very much, Ian. So hi, everyone. This presentation illustrates our position in genomic scenario, and specifically, I will be presenting our projects related to the integration of phenotype and genomic data using artificial intelligence tools for codification. I would like to start with a quick overview about BTAC in the genomic scenario, and after that, I will present the standardized studies and projects involving genomics that we are working on. BTAC is a corporate member of the Barcelona Health Hub since 2019. The purpose of this association is to promote innovation in digital health. The goal of BTAC in this field is unlocking the power of data through the use of standards. BTAC is also one of the founding members since 2015 of Bioinformatics Barcelona. This organization currently comprises 55 leading institutions related to the bioinformatics sector that develop their activities in the health, agri-food, and technology sector. One of the special working groups within Bioinformatics Barcelona is the Data Integration Group, of which BTAC is part of. It was created to analyze the problems associated with the integration of bioinformatics and clinical data, search for standards, and enhance collaborations among the members of a pilot project. This group consists of 30 people from different entities, hospitals, research centers, and universities, and companies. The multidisciplinary team, consisting of clinicians, geneticists, and bioinformaticians, have been working to achieve the challenge of genomic data integration in electronic health records. The group discussed about patient and genomics data sets, genomic interpretation, data storage and privacy, data access, archetypes, problems in the workflow, as well as solutions. Related to international participation, we belong to the SNOMED Genomics and Precision Medicine Clinical Reference Group. We also are part of the LOINC community and member of the Laboratory Committee. Both standards are evolving to support clinical genomics. I would like to mention 3 of our relevant studies involving genomics. The first one was performed in 2019 about standard terminologies in genomics on behalf of NHS Digital in UK. The goal of this project was to find out the international terminologies involving genomics to support a better personalized care and research. Along with NHS Digital, we created a survey for developers of terminologies, vocabularies, and data products to evaluate minimal requirements to support clinical genomics. The first line of the study included ontologies like HPO, disease ontology, or gene ontology, and genomic data products like OMIC, clinical variant, AGNC, and so on. At the same time, we developed a survey designed for these terminologies users to identify the usage patterns and trends in 3 different scenarios: rare diseases, cancer, and pharmacogenomics. From these studies, we estimated that the adoption of standards to represent phenotypes were strongly related to the domain. HPO, order, or OMIN are preferred for rare diseases. Clinical standards like SNOMED and LOINC are reported in oncology, and specific terminologies like CPIC are used in pharmacogenomics. Furthermore, the use of variant and gene identifiers also depends on the scenario or domain, and some of them are using a mixed variant type. We also obtain information about other relevant data, such as the usefulness of adopting standards, the limitation and boundaries, the use of cross-mappings, or the use of guidelines or recommendations for implementation like Global Alliance or FIRE. Using these preliminary results, a similar study was performed in Catalonia, including 4 real use cases coming from clinical current research. The goal was to identify in the genomic reporting, first, the relevant data sets and elements that must be included in electronic health records, and second, the use of patterns and gaps in the harmonization process comparing clinical care versus research. The results obtained are summarized in this slide. The phenotype standards are not yet implemented in clinical care comparing to research, where standards such as HPO, OMEM, or ORDO are well implemented. Related to orders, there is a need of a standardization of the genomic testing, specimen coverage, DNA platform used, methodologies, metrics, etc. And related to result, it's necessary to address the mix of gene and variant identifiers and to unify standards used to identify variant details and interpretations. To finish this part, I would like to mention our participation in real-world data projects. We are collating data that can support monitoring of cancer therapies based on genetic and molecular features following the EMA recommendations. For example, this one is focused on breast cancer and is a collaborative effort that comprises the collection of the data from different sources, laboratory data, pathology and molecular data, and routine testing, and clinical data from electronic records as demographics, comorbidities, or therapy responses. And normalization of the data. BTAC is providing standardized templates based on NOMED to collect the data, and our coding tool CityMap is used to normalize the data collected using different standards by domain. In the second part, I'm going to talk about our normalization projects in the Laboratory of Genomics. The one presented today focuses on exome testing. As the 85% of disease-causing mutations reside in the exome sequencing is becoming increasingly popular when other alternative methods fail to detect causal mutations. Some of the benefits of exome testing are establishing etiologic diagnosis for multi-gene causing diseases, timely medical management, avoid of additional testing, reproductive planning, and research opportunities. One of the most important challenges of the whole exome testing, we are talking about more than 90,000 genes, is that the DNA library preparation, it means the structure and composition of the target DNA, is not uniform. In addition, there are other issues, such as the selection of the relevant variants and the reporting of pathogenicity depends on the algorithm used, and the reporting on incidental findings. The adoption of the clinical exome sequencing, we are talking about 5,000 genes, can deal with these challenges, allowing an efficient preclassification and annotation of the variants and reducing the number of incidental findings, restricting the interpretation to virtual subpanels of genes. So, comparing to other massive approaches, the clinical exome study offers advantages in clinical care, reducing the cost of data analysis and interpretation of incidental findings. This is an example of the workflow in the Laboratory of Genomics when the phenotype triggers the laboratory order. When the phenotype suggests a syndrome with a large number of genes associated, two pathways follow. For cancer domain, a specific genetic panel is performed, and clinical exome sequencing is the first-line approach for the rest of Mendelian diseases. The whole exome sequencing is the approach for non-syndromic diseases, autism, and intellectual disability, when no genetic panel is available or when the rest of the previous genetic studies fail to detect causal mutations. In a few cases, whole genome sequencing can be performed for research purposes. In this scenario, the law terminology is supporting both orders and results, including codes for whole genome and exome testing. These codes include more than 60 associated observation to report different data, genetic disease assessed, variant details, and interpretations. Concerning panels, and due to the increasing demand, the Registry Institute is creating new codes for multi-gene analysis, especially in cancer domain. The first step to integrate exome data in the genomic laboratory workflow and to integrate to electronic health records is the identification of the relevant data sets and elements for orders and reports and their codification to international standards. Related to orders, in the last 2 years, we have received an increasingly demand for normalization of exome testing that comes from different Spanish hospitals and international laboratories. Our clients manage their own laboratory catalogs with the loin module of our coding tool CityMap through the user interface or through web services. Furthermore, CityMap allows the codification of phenotypes with SNOMED and ICDT modules. In this example, you can see a SNOMED codification. The terminology server allows to manage terminologies, subsets for specific domains, and cross maps between related terminologies. For example, this one between SNOMED and HPO for medullary thyroid carcinoma. This slide summarizes the CityMap functionalities. The 4 coding modules, LOIN, SNOMED, and ICD-10, diagnosis and procedures, and the semantic net with related terminologies through the terminology server. Concerning results, we collected the data from different genomic reports, and we could identify the relevant data sets and variables related to patient, genomic test performed, and their results. We identified the variables with LOIN codes and the answers with a 16 code systems or normalized value sets. Let's see an example. Here you are the variables to represent the variant found where LOIN codes identify the variables involved. We have also detected gaps in the terminology. To represent answers, a mix of code systems are necessary, globally accepted genetic identifiers like HGBS, set or normalized values like LOIN answers, or SNOMED codes to report associated phenotypes. For example, to report the clinical significance of the variant, we use this LOIN list of values, pathogenic, likely pathogenic, etc. At this point, we worked on an implementation consultancy project in one of the genomic laboratory of a public hospital in Madrid, creating a model of a structured genomic reporting. We started with the clinical exome reporting as it represents, together with cancer panels, the most frequent genomic testing in this laboratory. The disease assessed in a proven uremic hemolytic syndrome is recorded with an SNOMED code. These are the data related to the genetic test performed, coded in LOIC. And again, the phenotype information and the specimen used for the analysis is represented with a SNOMED. These are the data related to the variant report. In this case, 2 variants have been identified that are specified in detail. The methodology data were the variables related to the platform used and the computational analysis for interpretation are specified. And finally, the overall interpretation of the results, positive, negative, inconclusive, etc., observation for of the geneticist and genetic counseling. To develop our approach, we look at international frameworks for collecting, coding, and retrieving genetics data, specifically FHIR, and the recommendations related to semantic standards involved in sequencing data, interpretative genetic information, condition, context related to the patient and family members, and to describe the genetic order requested. This is a use case to retrieve, for example, all DNA sequences related mutation with an interpretation and non-significance using LOIN to identify the question or variable and the long answer to identify the answer. We also look at the Global Alliance recommendation to represent the sequence, even though it focused more on the needs of researchers, and the use of ontologies to capture phenotypes, as you can see in this chart. Some of them are already implemented in our CityMap platform. To see the complete circuit, I'm going to show you a model of integration of phenotypes data and genomics data using our CityMap tool. This is an example of an ataxia study for an index case patient. The request of the molecular study is launched by the neurologist from the hospital information system, selecting the type of the test, the medical specialty, the disease assessed, the case definition, and the specimen. The condition, ataxia, and the specimen, blood, queries the CityMap via web services and returns SNOMED city codes. CityMap contains subsets of SNOMED city codes by medical specialty and subsets of allowed specimens. These codes trigger the laboratory order, coded in LOINC, in the laboratory information system. In this case, a clinical exome study. This study generates a complex report that is converted in a structured and normalized genomic template. CityMap is a terminology server based on SNOMED that offers semantic net with other phenotype terminologies such as HPO or OMIN, and also can display genotype and sequence associations through standards such as Hugo, HGBS, or clinical variant. Currently, we are working on a NLP prototype based on SNOMED to extract phenotype information of the patient useful in the critical process of variant annotation. So, all the coded information from the hospital information system and the genomic template becomes part of the hospital data lake, allowing along with external knowledge databases like clinical assays, ontologies, clinical guidelines and recommendations, genomic databases, etc., create clinical decision super rules. In this example, a different diagnosis such as breast cancer launches a different request, the study of a breast genes panel plus MLPA technique. Finally, this is a screenshot of our NLP prototype. This tool is based on SNOMED in Spanish, and in its first version incorporates two hierarchies, clinical findings and procedures. Our next developments are going to focus on identifying molecular entities to support personalized medicine, as you can see in this example. The implementation of NLP techniques based on LOINC will be able to identify molecular testing and results for prognostic and treatment biomarkers. In this example, the negative result of this mutation relevant in a certain lung cancer subtype. In summary, the normalization of clinical and genomic data with global standards such as SNOMED, laboratory standards such as LOINC, and relevant standards in genomics such as HPO, ORFA, OMIN, UGO, HGBS, etc., is essential to enable efficient precision medicine. The use of artificial intelligence algorithms tools such as CityMap and NLP techniques allow the integration of relevant data from different sources in the electronic health records. This circuit will make it possible to establish decision support rules based on the hospital data lake and other external knowledge databases. So thank you very much for your attention.
So thank you, Gloria, for your presentation. Can I ask that the attendees just give us a moment while we switch over from our pre-recorded content so that Gloria can address your questions that you've been submitting live. Please note that this session will be available on the event platform for the next 3 months. Thank you. So this time we're live. So we'll do a bit of live Q&A. So I have a couple of questions for you to start the ball rolling, I guess. One question from me, which I'm quite interested in, and I've never spoken to you about this, so I'm intrigued at your answer. We obviously use and generate ourselves a number of maps from SNOMED or between SNOMED and other terminologies. And we're also in the process of, particularly in the genomic space, developing some further maps, so particularly between SNOMED and HPO initially. Do you use our maps, or do you use your own, or do you refine our maps? Do you make use of them?
Sí. Hold on, please. Si refinamos para los maps entre SNOMED, si los utilizamos, refinamos o como.
No, we are using the mappings, yeah.
Yeah,
we are using the mappings. We are not refining the mappings. No.
Okay.
We are using the source, always the source.
So if you could, if you had the power, so I'm giving you the power to link SNOMED to other genomic terminologies that the maps don't currently exist, what would be your top 2 or 3 that you wanted?
Yeah, we are using the mappings from SNOMED to HPO and ORFA, and we are waiting forward to incorporate the SNOMED and OMIN cross mappings. And to go to the genes, we are using HPO or ORFA. It depends. It depends on the disease. We are using all the cross mappings that the HPO or ORFA provide related to the associations between phenotypes and genes. We are using these cross mappings.
Okay. So obviously, one of the challenges with all of this is, particularly in genomics, there are a large number of standards in the area. I guess rather than you, this is more aimed at us. How could we support you better in terms of being standards development organizations, so SDOs? How could we work better together to support you?
Yeah, I have an idea. I think that you know, Ian, that we rely on you and your roadmap in developing these terminologies and cross maps, because we want to have in our terminology server something that is useful for the entire global community. So what we need is to know that all those cross maps are really maintained and updated regularly with some chronicity. So this is something that we are very interested in, not only using those contents that are really updated, because it's something that we cannot do, no? So relying on the sources and in the alignment on the sources, no? This is difficult, we think.
So as you know, the maps that we produce, we have formal agreements with the other SDOs, and part of that agreement is the maintenance of all those maps. So yes, we take that on board, and I share your concern. So the one area that you mentioned in your presentation is obviously sharing data across laboratories, not just within Spain, but essentially across borders. Do you find translation to be an issue or not? So are other languages problematic?
Yeah, about the translation, as we rely on the standards development organization supporting the lab tests, we try to use the linguistic variants that are periodically released in every update. Am I answering your question?
Yeah.
So it's a community effort in the end. It's not that someone is paying for a certain translation. It's the countries that are using that have adopted that terminology that are consequently following the new updates and the new translations of items or parts or tests that released in every release. So we have had, for example, we don't dare to help implement standards in a country that has not a translation, because we cannot use them, no?
Yeah, and for example, related with the law codes, we like to use the international edition because, for example, due to the pandemic time, we have a delay in the Spanish translation for a lot of terms related with COVID-19. So, especially with Loin, we always work with the international for mappings, the international edition. But our tool can display all the description in the different linguistic variants. But for mapping, we use the international version. Yeah. And it's not related to SNOMED, we incorporate in our terminology server the Catalan extension and the national extension and the international release.
Yes, we rely on the extensions until they are not uploaded to NRC, because this is content already translated and in usage in the territory. So we think it means to be in the terminology server.
Yeah.
So do you have, we obviously do in terms of National Release Centers, but do you have a formal link to the Spanish National Release Center to get some of that content promoted, if you like, either into the Spanish National Release or into the international release?
Yes, we are in conversations because you know that Spain is kind of peculiar regional health, no? 17 different regional healths with different linguistic variants. So we are talking with the Catalan government in order to be linked to the ministry. So they are in conversations. We talk with both, but it's something that we can be pushing, but not leading the governance, no?
Yeah.
So from my point of view, push harder. We would like that content in the international release, probably sooner rather than later. I think it'd be really helpful.
Yeah.
Obviously, with a lot of the genomics terminology, the focus is on rare diseases. So, with HPO, with OMIM. Have you done much exploration about using phenotypes to more common diseases? So, say phenotypes linked to coronary heart disease or diabetes, or is it limited to rare disease?
Sorry, I didn't understand the question.
No.
We understood
So
that you are
the work that you're doing. So a lot of the genomic terminologies focus on rare diseases. So HPO is provide phenotypes for rare diseases. Have you done much work which focuses on the more common diseases? So things like coronary heart disease or diabetes, rather than some of the rare disease.
No, at this moment we are focusing on rare diseases and oncology. At this moment,
yes, because there are three main initiatives in Spain evolving, maybe because of next generation funding related to precision medicine and oncology. So now we are focused on that.
Okay,
but it will be very interesting having these rare diseases. Next step.
Right. Well, I'm gonna bring this Q&A session to an end because, as you know, I'm moderating another session. So I'd like to thank you both for your presentation. And as always, I look forward to working with you for the rest of this year and into 2022.
Yes, we will.
But I'd like to thank you. And hopefully the audience have enjoyed the presentation and enjoyed the questions. And please go away and enjoy the rest of our expo. Thank you.
Thank you.
Thank you very much.
Bye.
Thank you.
Bye.
Bye now. Bye.